Hi, so in this video I'm gonna try to do something special. So I'm gonna try to do some maths for you today. So the inspiration came up from this little blog post here from my good friend Daniel Holden. He wrote this little blog post a little while ago, and there's some maths in there. It's really fun maths. Like if you're a gameplay programmer or like any person that wants to use maths in their daily lives, this is a good blog post with lots of like fun maths. And I want to do some of it for you today in a different way, because this is so fun. Like I'm having a lot of fun with solving the spring damper equation is a fun process that everybody should try. So we're gonna start right away with the main idea is that you have your position that you're gonna call p, which is a function of time. So p of t, you have a function p of t that you want to solve, and your goal is to go to some goal. So goal g, some position, so it's in one dimension. So you have let's say you have this like this position, and over time t, and you're here at p0, and you want to go towards your goal g, and you're gonna go towards this goal like this over time. So, and you want to smoothly go to there. So in gameplay programming or any like science or anything, you want to go somewhere. So you have targets like robotics or anything. It's always the same thing. You're somewhere and you want to go somewhere else. Like it's the basis of everything. It's like be at some state and try to go in other states. Like it's always this. So, and the trick is to have this other variable that you could call like position relative to goal. So you could call this like pos rel to goal. Let's call this x of t, which is p minus g. So then instead of having this, so let me kill this and write it again. Like instead it's going to be x. It's going to be a little bit easier. So you have x, you have time, and now you have this. You start at x0 with some velocity v0, and you're gonna go around like this and maybe oscillate around your goal, which is now 0. Your goal is now 0, and that simplifies. You don't have p and g, we just have x now. And you have velocity, vel, and it's v of t that we also want to solve. But let's forget about v and just remove this and say instead x prime, which is dxt dt, so derivative of the function x relative to time. So that's your velocity. And then there's the acceleration, which will be x prime prime of t. You can also say d2 dt squared of x of time. That's a t. Maybe I should try to have the can I erase with this? Oh, anyway. I did not erase the correct thing. Can I try it with this? Or this? Or this? No, there's no eraser. That's kind of sad. Erase. T. So I just bought this, so that's the reason. I'm just trying my little new toy now. So now you have an acceleration, and like the spring damper is, you have a force that brings you towards your goal, and also another force that's the other direction from your velocity that slows you down. So a viscosity and a stiffness. So the one way of seeing this is ouch, that was the worst drawing ever. Let's do like this, x again, and you're at 0 here, and there's like a spring with little mass there, and there's a force from the spring, and there's also another force like when you're going with this velocity, that's going to be in the other direction. So F equals ma, like let's call this x prime prime instead, and let's say the mass is 1, so we don't actually care about the mass. So let's kill the mass, and it's just the acceleration is just the force. And so what is it? Like it's gonna be like minus some stiffness, and if I'm gonna like follow a little bit the naming that he used in this blog post, so I'm gonna call, instead of saying K for stiffness, we're gonna say S for stiffness, so and X of t. Sx, and also another one which is also negative because it's in the other direction than the velocity, and with some damping. And we're gonna call the damping, it could be B or something, but let's call it 2y. For some reason, it's gonna be y the damping, but let's put a 2 in there. It's gonna make the equations a little bit easier, but not that much easier. So it's kind of cheating writing numbers here. I really hate it, like when teachers do that and put numbers in front of their variables because they say it's going to be easier later. It actually like makes me super sad and uneasy. Like, why did you put a 2 there and like rename this damping y? Anyway, I'm doing it now, sorry. So, and it's going to scale the velocity. So this is the equation that we're going to use. So it's actually, yeah, it's kind of sad that we have, what did I do there? There's just one little thing here. Maybe I could like write it like this instead, dx dt. So that's the thing we're trying to solve. We try to find a function, like our goal is to find x of t equals some big thing with t's inside there and some constants that like, and we also know the initial conditions. X at time 0, it equals x0, and x prime at 0, it equals v0, this v0 and x0. So that's our goal, like that's what we want. Let's find a function x of t. And now, like, we try to remember like how to solve differential equations if we've seen this in school, but we forgot everything. Let's say we forgot everything about derivatives. Okay, so I'm going to start with, like, I know, like, we can guess a solution. We know there's going to be exponentials in there. We know, like, in advance if we've seen that before, but let's forget everything about all we know. And we, like, hopefully at this point here, everything makes sense. This equation, you can actually feel what it means. Like, we're going in the opposite direction, making an acceleration, and we have some sort of viscosity. So this acceleration is in the opposite direction. So here, like, everything here makes perfect sense. But now we need to like guess a solution. But to guess a solution, you will need to say something like, okay, we know the solution has this form. And this makes me sad, like, to guess solutions. So we're gonna start and like do something else instead to build some intuitions about like why it's gonna be some exponentials and some sines and cosines that they're gonna come in here. So let's start from the beginning and just like practice a little bit of derivatives. So let's say I have this function. Let's say we have, we try to find the derivative with respect to t of this thing. Let's say t squared. What is this? Like, we remember like what it is, but let's say we forgot. Let's say we forgot what the derivative of this is. So what we're gonna do is, like, we know, like, this is gonna look like this. That's t squared. So we have t here, and that's t squared. And we know, like, the derivative here is positive. Here is also positive. So we know the derivative was gonna look a little bit like this because, yeah, positive here. So this slope is positive here also. But how did we find this again? So like what we actually want is, like, there's a little dt here and a little thing here. So the slope is this divided by this. There's a little dt here. And this is something we can compute. Like, it's this height minus this height. So this is the worst drawing ever. So let's forget about it and just write things. So this derivative is, what we want is, okay, let's still draw it somehow. So we have a t, and then here t plus dt, clack, and this is the function at t, and this is function as t plus dt. So we're gonna say the function at t plus dt is just t plus dt. So that's our function. There's a 3, now minus the functions at t, so it's just t3, and then the slope is divided by this. So we have this divided by this, so it's divided by dt. And so when we do this, let's actually do it, plus dt, and then when we do it once, it gives us t2 plus 2t dt plus dt2 minus t3 all over dt. So what I did here is just like, there's one of the multiplications here that I did, and then so we look at this and we do it again. So t3, there's now, like, so that I did this, now I'm gonna do this. There's 2t2, there's 2 t's, and then dt, and then the next one is this, so plus t dt2, and then this one is t2 dt, that's this. Now this is dt2 t dt, and then the last one is this one, so it's plus dt3. Let's not forget our little t3 here, and divide everything again. So it's just to just to start at the beginning. So let's gather the terms. Like what we had is like, that's the derivative t3 dt. There's a t3, and then plus the t2s. You see there's a t2 here, there's another one here, so that's 3 total. So 3 t2 dt, and then there's 2 t dt's and another t dt. That's a t dt2 probably. Yes, the last one, I forgot the 2 here. So 2 t dt2s and another t dt2. So there's also 3 t dt2s, and then finally the dt3 plus dt3, then minus t3, that was this one, and all divided by dt. So that's a derivative of a cubic function. So we see that we can kill this with this, and now there's one dt here is going to kill one of them. So I'm going to kill the dt by saying this is instead 2, and this is instead 1, and this is killed. So we see that it's 3 t2s plus 3t dt plus dt. And so this is the slope of the function, the cubic, and we see that when dt goes to 0, these die, and the only one that remain we stay with is this. So the derivative of cubic is this. So we see what happened. The 3 came in front, and this got like reduced by 1. So like just to make sure that we still have the intuition of what the derivative is for a polynomial. So when we have any function, so dt of something, some t to the something, we can prove that it's going to be the same thing, and it's going to be n t n minus 1. So it's just to remember this. And from this, we now introduce, like, let's say we have a function that looks like, let's try something, okay? I'm going to do something really magical there. So I have 1 plus t plus t squared on 2 plus t3 on 2 times 3 plus t4 2 times 3 times 4. So again, like this is like the leap of faith. I'm trying something here. I'm inventing this big thing, the big series, and we don't know why did I do that, but I just felt like it. I felt like writing this on the board now. And I say, like, try to find the derivative of this. So let's derivative of this. It's going to be each term independently. So derivative of 1, it's a constant, so slope is 0, so 0. Derivative of t, like what's the slope of this function t, which is just a line like this, it's going to be 1. Then derivative of this, so we bring the 2 in front, so it's going to be 2t. And then derivative of this, 3 in front, 3t, 2 times 3. 4 in front here, 4t, 2, 3, 4. And kills the 2, kills the 3s, kill the 4. And we end up with 1 plus t on 2 plus t on 2 times 3. So we see it's the same. So we took the derivative of this and we get the same thing. So it's like the identity function for derivation. So, and this is what we call an exponential. So this is e to the t. So that's kind of the definition of the exponential. It's also like the exponentiation of like anything. So that's a number here, but it's like the reason why the exponential is fun is because we have this function. And now I think we're ready to try something. We have this function here. Okay, let's do something else before. So let's say we have e to the something, like some number r t. So what is this? If we plug this instead of the t here, I'm going to put rt. So it's going to look like 1 plus rt plus rt squared over 2 plus rt 3 over 3 factorial. So these are factorials, obviously. So now what we see is when we try to derivate this, what happens exactly? So derivation of this plus derivative of this relative to t. So it's just r plus derivative of this relative to we have r2 here when the 2 goes in there, and then we do the same thing as before. So there's a 2 is gonna come and kill the other 2, so it's gonna be 2t over 2, so it's gonna still be just t. And now plus same thing here, r3 t2 over 2. So what do we have here? So what we can do with this is just, we're gonna, this was not a 1, this was a 0. So what we're gonna do is just like remove one r from all of this. So it's gonna be r times the rest of it when we remove one r. So it's gonna be 1 plus rt plus this, remove one of the r's in there, so it's going to be rt squared actually, 2 plus blah blah blah. So we see that we get the same thing as here. So the derivative, like this is dt of e rt, is actually just r e rt. So when we like find a derivative on exponential, we pick what we had here and put it in front. That's what an exponential does when we try to find a derivative. So that's why it's really fun. And that's why we're happy and we really like exponentials. And that's why there's exponentials everywhere. When we have a differential equation, we see this, you know you want to try an exponential. That's the first thing that comes to mind. You know exponentials are fun because of all I just showed, and this is the magic of it, and that's it. Like that there's nothing more to it. And then like you see the differential equation, try an exponential, see what happens. So let's do it. So let's I'm gonna just rewrite this here. So I'm gonna have, that's what we try to solve, x prime prime plus I'm gonna like do see this here, I'm gonna bring those to the other side and say equals 0 instead. So there's minus, the minus here is gonna become positive. So let's put everything, we just say 0 equals, we said 2y x prime plus sx. So this is what we try to solve. Oh, sorry. Try to solve this. And we want now to try something. So when we try to solve differential equations, there's going to be constants. There's going to be like constants in the actual solution that we're going to find by looking at the initial conditions. But for now, we just find solutions. Find like some equations that fit in there. So we're going to try x of t. Let's try exponential of something, some number here that we'll try to find, t. So that's our guess. And we just try it in there and see what happens. So first we find the derivatives. So because we'll need it here and here. So x prime, we said when we find the derivative of this, it brings an r in front, r here, like prime, r squared, e r t. So the first thing you do, like find the derivative of your guess, you see r came here, the only like we're trying to find derivative relative to t, so that brings another t here. That's why there's a 2 here, the second r came here. So now we just plug this in there. So we're going to plug this here, plug this here, and plug this whole thing here. So what happens? It's 0 equals this one. It's this, r2 e rt, plus this one, r e rt, and this one plus e rt. Oh, I forgot the 2 y's. Let's start over. It's important to not forget this. That was the constant for viscosity. Our viscosity constant is called 2y for some reason. Bear with me. And then, so r e r t plus s e r t. And now we see this and we're like, okay, so there's a 0, so there's those everywhere, so we can just kill them. Boom, boom, because yeah, 0. So we can divide the whole thing by this. So we're left with r2 plus 2y plus s. And now we see this and we tried, oh, I forgot the r. And now our goal is to find the r. Actually, we try to find this equation here, find constants. Like we had to put a constant here, and our goal is to find it. So we need to find r. So if we want to isolate or like solve for r, this here, we see it's a quadratic. So let's say you forgot how quadratics work, because we don't want to take anything for granted. We know it's like minus b plus minus square root b2 minus 4ac or 2a, or let's say you forgot that. So you just need to know like that you want to isolate r. There needs to be just one r here, not 2, and not the little 2 here. It's going to be just 1. So we can say it's going to be, this needs to be equal to something squared plus some other constant. So let's call it like some number. So it's going to be like r plus some number. Let's say let's come up with variable names like just m and n. Okay, now and now m and n, we need to find them. so that it looks like this. So let's just like open this. So it's going to be R2 plus 2RM plus M2 plus N. And now like I try to put this in this form. So it's almost there. So it's just R2 plus 2M R plus M2 plus N. So this guy and this guy, you see like it's this. Like this guy, 2Y is this and S is this. Okay, so it means 2Y needs to be equals to 2M. So M is just Y. And then, so, and M2 plus N, this is S. The goal was to find M and N. So we have M, we can plug it here, like this M, so it's just Y squared plus N. Oh, not enough room anymore. Let's bring this bigger. So we're here. I just said that M is Y. And now our goal is to actually find N. So N is... I need to bring the Y to the other side. So it's going to be S minus Y squared. So we have our N and we have our M that we need to plug in there. Now, so let's try that. So it's 0 equals R plus M is Y squared plus N is S minus Y squared. And now we're happy because there's just one R. The goal was to transform this into a form where there's just one R so we can isolate it. So you see, we can like solve for R easily from here. Now, that was impossible because it's a quadratic, and now we can with this. So we completed the square, so that for those who forgot what completing the square is, so now we're happy, we can really feel and understand everything. So now I just solve R for this. So I'm going to bring this the other side. So it's going to be Y squared minus S equals this. And when you want to solve for a square like this, like what are the values that give this? When you bring the 2 the other side, what you need to do is square root 2 minus S equals R plus Y. And but there's 2 solutions also, plus or minus, because minus this, when you square it, it's going to do also the same thing. So now, so R equals, I'm going to bring the Y the other side, so with the minus, so minus Y plus minus square root Y2 minus S. So that's where we end up. So that's our R, we solved for it, and our goal is now to plug it in here. So that's our solution, we have it. So I'm going to just say X, now X of t equals exponential of this minus Y plus or minus square root Y squared minus S times t. So that's our solution that we found. So now what do we do with it? So we have 2 solutions actually. There's x1 and x2. So the actual solution, when you look at this, if one solution, go back to this, if we have one solution, like a scaling of this solution also works. So any like number in front of it would also work because it would cancel out because there's a 0, like it's homogeneous differential equation. And if there's a sum of the 2 solutions would also work. So you see if like a sum of the 2 solutions would work, because you see it's all like, there's no constant here. It's all like if, so actually our solution is in general, so X of t would be some constant time our first solution plus, okay, let's call this something. So I'm going to call this guy, so square root of y squared minus s. So I'm gonna just not think too much about like what happens if it's negative for now. Like obviously if this ends up negative, it's square root of a negative number, there's gonna be some imaginary numbers there, but let's not think too much about that for now. So I'm gonna just call this, let's say w. So it's gonna be plus w times t. And our second solution is with some other constant, c2 e minus y minus w t. So that's our like solution now. So we actually found one of the constants. It was the r thing that we found, but now we need to find c1 and c2, and for this we'll need our like our boundary conditions, this x at time 0 and at the velocity at time 0 and position at time 0, so that we can start our nice little oscillation there. So that's our goal now. So we can actually find the first one pretty easily, I guess. If we just plug 0 in there, what happens? You see an exponential of 0. Exponential of 0, what does it do? Exponential of 0. See, exponential is this. When we plug it at t equals 0, it's just 1. So exponential of 0, it's just 1. So it means that x0, it equals to just c1 plus c2. You see, this became 1 and this became 1, so it's just this. So we actually just have one constant, because I can just put c2 equals x is not minus c1. So I can just plug this in here. So let's try that. So now our solution looks like this. X of t equals c1 e minus y plus like t plus x0 minus c1 e. You know what? I don't actually care too much about this. This makes me sad. I don't really want to do that. Like, it's not necessary. Let's keep it like it is, and instead do something else. You see here, like when you have an exponential of like, let's say like 2 to the 3 plus like 2, like this 2 to the 5. So that's 2 times 2 times 2, it gives I think it's 32. 2, 4, 8, 16, 32. But it's actually all the same as 2 to the 3 times 2 to the 2, which is 8 times 4. So you see, when you have this, you can also say it like this. You can just separate the sum here, an exponential, it's always like this. So e is the same. So this, I'm going to separate it. It's going to be like minus yt, and then e wt. And let's keep it the c2 as it is, because I'm happy with c2 now. So e minus yt and e minus wt. It's this one here. So I just separated like this. You see the t came inside, and I separated the two exponentials. And the goal was to like bring this one, you see it's the same in both, so I can put it outside. So that was what I wanted to do now. Yt, and then c1 e wt plus c2 e minus wt. And now I'm more happy. I like this equation, because this gives us some feeling for what the solution looks like. Because you see, there's this in front, so it's gonna look like a decreasing exponential that's gonna like scale some maybe oscillation, and this gonna be either an oscillation when it's underdamped, or it's gonna stay real and just be overdamped. So now we still have to solve our constant. So that c2 is there, but we need c1. So for this, we need to find the derivative of this and plug our v naught, the velocity at 0. So for this, we need prime of this. So now we're in we need to differentiate this, and this is dangerous because it could get messy because it's a big thing and we need to differentiate it, but it's not too bad. So we need to remember the product rule for differentiation. So we're going to differentiate this one and times this, and then keep this one the same and differentiate this one. So what happens when I differentiate this? It gives me minus y e minus yt, then times c1 e wt plus c2 e minus wt. And then the second part is this one stays the same, e minus t times c1. Differentiated this brings a w in front of it. W e wt plus this one. It becomes c2 minus w. This one came in front of it. E minus t, like this. So that's our differentiation of this. And this is the most messy that's going to get. Like everything here was not too difficult, not too messy, but this one was hard. Like it's the hardest thing we've done, but it's still not too hard. Like it's really like actually pretty easy, but it's just we need to keep track of what's happening. And now we want to try it at t equals 0. T equals 0 now because we know like that x prime at 0, we call it v0. Because it's one of our initial constant. We're here, like we know that we start with this velocity. And we have this, that we need to plug 0 in there. So what happens when we plug 0? Like this one, it's gonna, all the e's become 1s. Like it's just 1s everywhere. So it's gonna be minus y times 1. And this is 1, so it's c1 plus c2. And then this is 1 also, so 1, and this is c1, there's a w here, this is 0, this is 0, so, and this is, so minus c2w. So that's, and we see that this is equal to v0 now. And now we want to isolate the constant that we want, and we know that c2 is this x0 minus c1. Maybe we could put it right now. So we want to try c2 equals x naught minus c1. Okay, let's just try. The c2 was x naught minus c1 and plug this in here maybe. Maybe we should have done that before, but whatever. Okay, c1 plus x naught minus c1. X naught minus c1, okay, plus the other one, we don't actually care about the parentheses, c1 minus c2, like this c2 here is now this 0 minus c1 w, like this. Okay. Let's bring all this together. So minus y c1 plus y x0 minus y c1 plus c1 w minus x naught w. This one comes with this one. Minus, that's a plus. And c1 w. So that's what we have now. Okay, this is big, but we can manage. Like there's some, hopefully something cancels out. This, are we happy? Like this is stupid. Why? What did I do here? Like this is not there anymore. Like this died. What? I should not have done that. So this is already dead, and there's just this, and there's this, and this, and there was a mistake here in the signs. The sign here is wrong. Like this is minus. Sorry for all this. This is minus. So let's just clean this up. Minus y x0 plus c1 w. There's two of those. 1, 2. So let's put a 2 in front. Plus 2 c1 w. Is that right? Okay, let's try that. And minus x0 w. That's v0. So now what we actually want is isolate c1. So let's bring everything the other side. So v0 0 plus y x 0. This one, the other side is going to become plus x0 w. This is equal to c1w. What we actually want is c1 and bring the 2w the other side. 2w, and we got it. We have our c1 constant. So, and let's just remember c2 again was x0 minus c1. So we have this, we can plug this in c2, and we have our c2s and c1s. And maybe just for fun, we could like write this again, but let's actually not. Like we see this, we have our w's that are that is this, we have that, and we plug these constants, and we've solved our equation. Without thinking too much about like sines and cosines, just exponentials. So this will work out of the box for probably the overdamped case. The overdamped case is when this is real. Like this means that the damping, this is why it was the damping, is big enough. So it's bigger than, like damping here squared is bigger than the stiffness. So it means there's going to be no oscillations. It's like super damped, so overdamped, so there's no oscillation. So this is the solution for the overdamped one. So now if we want to do the underdamped, so this is going to be, this one's going to have an imaginary term. You could do some like weird math to convert the exponentials into sines and cosines, and that's really fun. But there's another way. We can just like start over and just instead of plugging sines, exponentials, we could like directly plug what we think the solution would look like, because we know it's going to actually look like something like exponential of something. That's going to be our solution, x of t, times, let's say, a cosine of something, something here. Some other, let's say another, let's say we don't know what it is, like the constant, some other constant here. So we could try this right away. We could try this in our equation and assume that this is positive. It's negative. This is negative. Let's say this is negative. So and try this in our solution, in our equation. So if we, right away we try this, we can see like it's gonna actually look like a nice exponential. It goes down and it clamps a nice function. And then the other solution could be e or t sine of some constant. And now the goal would be to find this constant. Like spoiler alert, it's gonna be super simple. It's gonna probably be the omega, the w here, but we should like make sure of this. So that's the exercise. The exercise for you now, like, is to go like do what I did here. Try to do the same kind of thing, but instead of using exponential, like just try to plug this. So what happens if you try to plug this in our equation? Okay, again, our equation is prime plus 2 yx prime plus sx, it's equals 0. So we want to try this and see what lambda is, what r is, and try to do the same like kind of process. And then try the like the sum of these two with some constants, c1 and c2, and try to isolate c1 and c2 like I just did here. And you'll find some equations for c1 and c2 using these. So you'll need to remember that the derivative over t of a cosine of like lambda t is equal to sine, but bringing in the lambda in front of it, which looks a little bit like an exponential, but it switches cosine from sine. And when you do it with the sine, it's the same thing, but with a minus. So doing that, I think you're like in business to like find the equation. Like just try to reproduce what I did here, and remember this little rule here. Find constants in front of these two solutions. The problem now is when this is 0, there's going to be just one solution. So you see here, if w is 0, what happens with our nice little solution? Like this is 0. So it means it's the same. Like you see here, this here, the W is 0. So all of this becomes just C1 plus C2, and like we lose what did I just, yeah, it's like the same solution. We have the same solution twice. Here you see this is the same as this when W is 0. So there's going to be just one constant. So that means we don't have enough freedom like to align it with the two numbers. We have two numbers, so it's two equations. We need two unknowns, two equations. So there's going to be one missing solution. And for this, it's like the critically damped. We need to know that there's another possible solution, and that's a fun one. And I guess I'm gonna do it in another video because it's a fun one to try. But like the spoiler is that in this case, when this is 0, try it at home. Like that's not another fun exercise. Try to prove that this some number here, I guess W will be so some number here. Yes, find a number here. Like let's go. Spoiler is gonna probably be y minus y t. So this is also a solution when y squared equals s. So this is critically damped. Critical. This damping squared matches stiffness. It's critically damped. It won't oscillate, but it's like just at the limit of starting an oscillation. And this is also a solution in this case. So there's going to be two solutions. There's going to be the E minus YT times some constant plus another constant T, E minus YT. So try this also. So that's the two exercise. Find the underdamped and critically damped. Find the C1 and C2, and then you can reproduce this blog post really easily. So if you look at this blog post, like what I explained is explained in a different way. You can look at all this. It's really, really nice blog post. But when you get here, like this is like that's one way of doing it. So what I showed is a different way. I think it looks more like what you would learn in a differential equation course. This is really like trying to make it look like what game people are used to with the lerps and the half-lives, and all this is really cool. And the fast negev, like that's so like that makes it work. And then it becomes really, really nice and useful. But yeah, so that was like another way of attacking the problem, like with just really like math, just the pure math version of this blog post. And yeah, I'm putting this all together, you end up with like super like nice fast code that just evaluates the spring damper with any DT, like completely DT independent, no explosion, because that's when the danger is, when you just do the most basic thing, like just advancing the velocity and the position without thinking too much, you could explode and be very non-DT independent. But in the end, you end up with this. That's the code. You can just plug this code in your engine, and you have a fast spring damper that really works. And you can then smooth out anything you have in your game. Like you want to smooth out something, just just like copy paste this, and you're good. But that was like a little bit of the math that gives some intuition why this math can actually work. So that was what I wanted to say today. So I guess like the next step, I guess if I was not lazy, I would actually do it and show the solutions directly for the critically damped and underdamped. But yeah, please try to do it yourself. Okay, bye. That's it for now.